So I don't know if that will work because of how I have this set up, but if it does, then it will record the lecture, the audio and screen, and then it will appear on YouTube. Okay, so let's start. First, it has come to my attention some people might not have the correct textbook or the textbook at all. So for the first homework assignment, since those problems are selected from the textbook, if you look on the web page for the course, which is right here, there's a link to, so here's the web page for the course. There's a link to homework that I just made, and in there is a description of the homework itself. And then I made a little link here, which goes to a album in my Picasa web albums or whatever thing, which is the problems for this particular homework set. So I just took pictures of those pages of the textbook that I had sitting in my office. Okay? So some people might find that useful. Because the textbook for the course is by Poole, not the other one. There's two different texts that are used that look almost the same. And also these are the correct problems for this edition. Okay? That was the most frequently asked question. Any questions other than that? Yes? I have not made a way for you to read the class notes yet. But apparently it's very unusual for anyone to make class notes available at all. So I hope you can wait a couple of days before. But there'll be a website called cloud.sagemath.org where you'll be able to view the class notes. And I'm also going to export them to an HTML format, so they'll be directly viewable. But I simply haven't had time to write the code that does that. Sorry. So basically wait about, probably should be available on Monday, but maybe Wednesday, depending on how much time I have. Okay, so what we're going to talk about, oh, any other questions before I start? Yes?
Just a quick thing, is there like a catalyst, like map 308, like that's supposed to show up? Is that like new classes?
I don't know, I certainly am.
It's just me or
Okay, I don't know why that is. Definitely the class exists. And when I go to my UW, I see 308 there, so and a place to give you a grade, I think. I don't know. You can send me your name if you're worried about whether or not you're actually enrolled. And I can check on my list that I have. Did you get an email from me about the homework assignment? I took that from the list that I get at my UW. And I just sent it directly from a Gmail account because it takes 24 hours at least before they set up the mailing list. I saw another hand. Yes? I have not, but they'll be roughly equally spaced. So almost exactly 1/3 of the way through will be midterm 1. 1/3 of the way after that, midterm 2. And then there'll be the final at this scheduled time. But I haven't computed what those 2 days are. But thanks for the reminder. Okay, so any more questions? There's going to be a lot. Okay, so what we'll talk about today is actually solving systems of linear equations using echelon forms. So the goal by the end is that you understand how this process works. So understand how to solve systems using echelon form. It's really only a matter of time until this chain causes me to go flying, so I'm scared of this. Better be careful. I mean, this is really dangerous. I'll get a key to unlock this. Alright, so that's the goal for today. That's it. No more, no less. We just want to figure out how to take a system of linear equations like this, turn it into something involving a matrix, namely that, and then do something with the matrix and read off the solutions. There's some subtleties though, because there might be no solutions at all. There might be exactly one solution. There might be a one-parameter family of solutions, a two-parameter family of solutions, and so on. So you have to know how to systematically, quickly read off which happens. We'll take these two examples first and carefully go through them and see how everything works with those examples, and then see what to do in general, and in some related examples. Okay? By the way, using the program Sage I mentioned before, this is the code that you type in order to solve those systems. So there's a command called solve that you give it a list of equations and the variables you want to solve for, and then it gives you back the solution. Possibly, in the second case, there are infinitely many solutions, and they're written in terms of some new variable, R1, that just pops into existence. So just mentioning that that exists. Okay, so let's do it step by step for the first example. X1 plus 2x2 equals 3. And then 4x1 plus 5x2 equals 6. All right, so we're going to solve this system of linear equations. The process that we're going to perform will be something that makes sense in a lot of generality, and we'll just see what we get. So the first thing you do is you take the system of equations, and so one thing we had done before is we had rewritten it as a matrix equation, but you can kind of shortcut that and write this as a single, what's called augmented matrix. 1, 2, 3, 4, 5, 6. So sometimes this is drawn with a little line to indicate that you've stuck on an extra column. This is a single matrix, and it, by working with this one matrix, we can keep track of what happens both on the left-hand side and the right-hand side of this equation all at once. So what we're going to do to this matrix is the three operations that we came to at the end last time. Namely, we'll do things like rescale a row, add a multiple of one row to another, or swap the positions of two rows. So remember, those are the operations you can use to try to put a matrix in echelon form. So rescale row, swap rows, add row to another row. Those are exactly the same things that you can do to a system of linear equations that give you back another system with precisely the same solutions. If I take this system and rescale a row, it doesn't change the solutions. If I swap the order, it doesn't change the solutions. If I add one equation to another, it doesn't change the set of solutions. Okay, so we're going to take this matrix and simply transform it to a nicer form. Namely, we'll put it in reduced row echelon form, and then we'll read off the system corresponding to that matrix, and it will be very easy to see exactly what all the solutions are after we've done that. Okay, so step one, write down the augmented matrix corresponding to the system. Here's the system, here's the matrix. That's step one. And here it is in general for an arbitrary m by n matrix left over from the previous hour. Any questions? It's just a cleaner way. I mean, you could do everything with the original linear system, but it's really tedious because you have all these extra variables all over the place. Really silly. So we work with this instead. It's just you're abstracting out the essential information. Okay, so let's put this in reduced row echelon form. Those are the things you're allowed to do. There's no particular order in which you have to do them. You can do, basically you just have to figure out how to do them in such a way that you end up in reduced row echelon form, and anyone who does that will always end up with the same form. So let's just do something. So anyone want to suggest an operation to improve the situation with this matrix? Yes? Sure. Okay, we'll add minus 4 times the first row to the second row. So that gives us, we're just going to leave the first row alone. Minus 4 times the first row, you get a 0 here. Minus 8 plus 5 is minus 3. Minus 12 plus 6 is minus 6. Okay, so that's better. Okay, what do you want to do next? Yes? Sure, let's divide the bottom row by minus 3. And now we'll get 1, 2, 3 on the top. Doesn't change. 0, 1, 2. Great. Okay, what do you want to do next? I'm putting this in reduced row echelon form. Somebody else. So those are your moves. This is not in reduced row echelon form. Why is this not in reduced row echelon form?
Because of the 2.
Because of the 2. Okay. You think of a way to dispense with this 2.
You just subtract the second row from the first row 2 times.
Exactly. So subtract the second row, or minus 2 times the second row from the first row. Okay, so we'll just take minus 2 times the second row and subtract it. And that gets us to a matrix with entries 1, 0. Minus 2 times that 2 is minus 4. So we have a minus 1 there, and then 0, 1, 2. So it's probably better to think of it as multiply by minus 2 and then add. That's what we're doing. Okay, that matrix, is that in reduced row echelon form? Yes. In the process of doing this, I've gone from one matrix to another, and the operations I've done don't change the set of solutions to the corresponding system of equations. So over here, the system of equations that corresponds to this augmented matrix via this correspondence right here is x1 equals minus 1 and x2 equals 2. Would you agree that it's really easy to solve this system of equations? I mean, you'd have to be really, really dense to not be able to solve this. Because look, x1 is minus 1, x2 is 2. The only possibility. So the set of solutions, solution set is the set consisting of the pair minus 1, 2. That's the only point that solves this, or the only point that is on the intersection of the lines corresponding to these two equations. Okay? This makes sense in a lot of generality for all kinds of systems. You can do exactly the same process for a much bigger matrix, and at the end, if you take this matrix right here and put it in reduced row echelon form, it should be very easy to read off all of the solutions to the corresponding system. Okay? Let's do another example. Any questions? Only thing that makes this hard are two things. One, very, very hard to actually perform the echelon form algorithm without making a mistake. I mean, you have to do so many arithmetic operations, which computers can do like, I don't know, 1 billion arithmetic operations a second correctly, and humans can barely do one if they're lucky. So there's a big chance that you'll make a mistake there. The other part, which is much more interesting, is once you arrive at this, you have to think a little bit about how to write down all the solutions. This time, you didn't have to think much. But in some cases, there's no solutions at all, and you'll end up with something where you have to think a little. Or there might be infinitely many solutions, for example, and then you have to think a little bit as well. Yes?
What does the total stand for?
For me, that just means equivalent.
Okay.
So I have two matrices, A and B, and I write A tilde B. At least for the purposes of this, I just mean that I'm getting from one to the other via applying a row operation. Maybe, since there's kind of a direction involved here, I'll put a little arrow. It's not a formal, I'm not formally defining that.
Okay.
But I just want to emphasize I'm going from one to the next. Okay? So this is just, well, I don't want to put it over here. It's just, all I mean here is I'm going from one to the next. And there's some relationship between the various matrices on the board. Yes?
You had a row of all zeros except for the last one every zero.
Yes.
What does that mean?
That would mean there are no solutions to the equation. So, I mean, literally, you just read off the corresponding. Here, let's write a couple of augmented matrices in reduced row echelon form and then read off the corresponding system of linear equations. So here's an example of what you just asked about. Actually, that's not in reduced row echelon form. That isn't either. But that is. Okay. So, what's the corresponding system here? It's x1 equals 0 and 0 equals 1. Yes?
Why does that not move the-
Oh, just because,
with the 5 and 7?
well, it was in echelon form, but not reduced row echelon form. In reduced row echelon form, you want all of the leading entries to be 1. And when you look at a column with a leading entry, you have to clear it. So I show all zeros. So this is the corresponding system of equations. Are there any numbers? I mean, you can't find x1 and x2 that satisfy these two equations because The second equation is 0 equals 1, which has no solutions at all, no matter what values of x1 and x2 you plug in. Okay, so that's what would happen in your example. You have no solutions. So here there are no solutions. So I'll try another one. I mean, again, remember there aren't very many possibilities for what this matrix might look like. But we could do 0, 0, and it could be, oops, 0, 7. Is that in reduced to echelon form? Yep. And now you can write down the corresponding system. It's x1 plus 5x2 equals 7, and then 0 equals 0. So here, again, it's supposed to be very easy to read off all solutions. This one's a little more complicated because there are infinitely many solutions. But what you do is you take one of the variables, let's say x2, and you call it t, and then you write everything in terms of that. So here, we'll let x2 equal to t, and now we can write, now we have to solve for x1 and x2. So we've already solved for so solve for x1, x1 equals 7 minus 5t. And there you are, the solutions to this equation, the system of equations, are the set of pairs 7 minus 5t and t, where t is any number. I'm being vague about what I mean by a number, because it depends on where you're looking for solutions, but often in this class it would be the collection of all real numbers. I've heard that some people might not be very happy with set notation, so just in case you're not, what this means is it's all pairs given by this formula where t varies over all possibilities for numbers. So it's everything in that form. There's a lot of different ways you could write that. So geometrically, if you were to plot all pairs like this in the plane, you get a line. Actually, I can probably illustrate that. There's a parametric plot command in Sage. So I think seven minus 5t, t, I'll make t go from -2 to 2, maybe. I don't think I've ever used this command before. Hey, look, there it is. So what that is that's a picture of all points you get in the plane of the form 7 minus 5t, comma t, where t varies from -2 to 2. Like if you just computed a bunch of values like that, you get a whole bunch of points, and if you plot them, that's what you see. It's just a line, in case you're seeing in the back right corner. Straight line. Okay, so that's the set of solutions here. And we'll see more examples where you have infinitely many solutions where the matrix is bigger. You can't really have that many when it's only a 2 by 2 matrix. All right, so step 2 is to put it in echelon form. And step 3 is to read off the solution. All right, so let's just do the whole thing again, but for a 3 by 3, or a system of 3 linear equations and 3 unknowns. Okay, any questions before we do that? Okay. So here, I'll just write the matrix. I won't write the system of equations, but they're equivalent to each other. So 1, 2, 3, 2, and then 3, 4, 5, 4, and then 6, 7, 8, 7. Okay, so again, this 3 by 4 matrix corresponds to a system of 3 linear equations and 3 unknowns. The b sub i's are the numbers 2, 4, and 7, and the coefficients on the left of the linear system of equations are given here. All right? And this is my favorite 3 by 3 matrix. 1, 2, 3. Actually, no, it isn't, because there's a 3 there. Well, it's not my most favorite matrix, but my favorite 3 by 3 matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9. right, so let's put it in reduced row echelon form. You do the same thing. So I'm not going to show you every step, but you take this one, for example, and you add -3 times it to the second row, and you get something. And you add -6 times it to the third row, and you get something. And you end up with the leading coefficients of these two rows equal to 0, or the first coefficients of these two rows equal to 0. And then you continue along in that way. Maybe we should do this one. I don't want to do a million of these by hand, but we'll do this one. Okay, so I'll take -3 times the first row and add it to the second one. I get a 0, and then -2, and -4. I'll surely make a mistake, so watch carefully. -2. And then we'll do the same with -6 to clear the third row's first column. 0, -12, so that's -5, -18 and 8, so that's -10, and -12, it should be -5. Okay? And now, we basically now just take the next entry, the next row, take its leading coefficient, rescale the row so that you get a 1 here, and then use it to clear the column. You just repeat that, and eventually you end up in echelon form. That's one of many algorithms for putting a matrix in reduced row echelon form. There are many, many subtle and surprising algorithms for doing this stuff. So rescaling this row, everything stays exactly the same except that one row. So this one row changes to 0, 1, 2, 1. And just for fun, I'm going to rescale the third row too. While I'm at it, 0, 1, 2, 1. It's exactly the same. So now, I will take and add -2 times the second row to the first row. I want to clear the entire column to put it in reduced row echelon form. Okay, so I'm taking -2 times the second row and adding that to the first row. So I get 1, 0, -1, 0. And then 0, 1, 2, 1, 0, 1, 2, 1. Did I get that right? Okay. And now I will add -1 times the second row to the third row. And I'll just get a row of zeros. All right, is this in reduced row echelon form or not? Yep. All the leading coefficients, or the leading entries are all 1. You have zeros everywhere else in those columns. Okay, so we should now be able to read off. If we write down the corresponding system of linear equations, it should be straightforward to read off all solutions. So let's do that. The system is x1 minus x3 equals 0, and x2 plus 2x3 equal to 1. So here again, you have infinitely many solutions. What you do is you write everything in terms of this x3. In general, the way it works is, so define the, I have a little slide about this, so I'll pull this up. Pivot columns. So there's two different types of columns that you find in a matrix that you put in reduced row echelon form. The pivot columns are the columns that contain one of these leading ones. So that's a definition. The pivot columns are the columns that contain a leading one. Pivot columns contain a leading one. And then there are the other columns on the left-hand side of this matrix, so this one right here, that doesn't contain a leading one. So that's a non-pivot column. I don't really need to define it, it just means not a pivot column. So the variables that you can write everything else in terms of exactly correspond to the non-pivot columns. If you have 10 non-pivot columns, then you'll have 10 variables that can be anything you want, and you can write everything else in terms of them. Okay? So in this case, we'll just let, say, x3 equal to some new variable we'll call t. We'll solve for everything in terms of t now. So the set of all solutions, well, you can just write x1 as x3, which is equal to t, and x2 is minus 2x3, which is minus 2t. So the set of solutions are the triples t minus 2t. I think I messed up. I definitely messed up because I forgot that one. 1 minus 2t and t. So solution is the set of all triples t, comma, 1 minus 2t, comma t, for any t. All right? Yes?
All right, perfectly.
Yes?
So the pivot columns, the leading one, those are the variables that you write as variable one.
No, it's the other way around. Yeah. So there's exactly one non-pivot column here, and so I have exactly one independent variable, and I can write everything else in terms of that one independent variable. So, yeah. By the way, geometrically, what is this? If you were to just plot all of these points, what would you see in front of you? Nope, not a plane. Yes, it's a line. Yep. If you were to, you just vary over lots of different values of t, you'll get a line. It's a one-dimensional object because there's one parameter. Dimension is just the number of independent parameters. Like when you talk about a robot being 7-dimensional or something, you mean that there's 7 different parameters that specify the orientation of and position of the robot. So here there's one parameter, so this is one-dimensional. If there were 2 non-pivot columns, so you had to introduce 2 parameters, maybe you could call them S and T, then there would be a 2-dimensional space of solutions, and then when you were to plot the corresponding solution set, it would look like a plane somewhere in space. But in this case, it's just one. And the next slide is about that. Just going to zoom in a little. So there are lots of different possibilities for the structure of the set of solutions. It's possible, as we've seen already, that you might have no solutions at all. That's what happens, for example, when you end up with an equation like 0 equals 1 at the end. Another possibility is that you have a unique solution, and we saw that in our first example, where when you put the thing in reduced row echelon form and look at the corresponding system, it's just x1 equals a number, x2 equals a number, x3 equals a number. You just read off the solution. That's the case of a unique solution. Another possibility is that there's one parameter that you can write all the solutions in terms of. That's what we're seeing here. That happens when you have exactly one non-pivot column. Then everything can be written in terms of one variable. You can choose any value you want for that one variable, and you've parameterized all the solutions in terms of that one variable. Another thing can happen. Maybe there's 2 non-pivot columns, and then you can write all the solutions in terms of those 2 non-pivot, in terms of the variables corresponding to those 2 non-pivot columns. Or there might be 3 non-pivot columns, and you can write the solutions in terms of those. And in each case, the dimension of the set of solutions gets bigger and bigger and bigger. But it's nice because this is a nice, clean classification of all possibilities for what the collection of solutions to a system of linear equations looks like. And moreover, there's a good systematic process for finding the collection of solutions to such equations. In mathematics, there's lots of different types of systems of equations, or even just equations. And most of the time, it's very hard to give a complete classification for what the possibilities are for what those solutions look like. And even if you can, you might not be able to produce a procedure that systematically gives you all of the solutions. But here we're very lucky, because with linear equations, there's a way to get them all, and you know exactly what the possibilities are. Just to give you an example of something that was much harder, if someone were to write down, I don't know, a random looking equation something like, say, x to the power of 13 plus 17 times y to the power of 5 equals 3, and ask what are all of the solutions where x and y are rational numbers, then it's an extremely difficult theorem for which Gerd Faltines won the Fields Medal, that there are only finitely many solutions. And there's no known algorithm that will give you those finitely many solutions. It's an open problem to give all the rational solutions to pretty much any equation of degree bigger than 2 that you write down. And if you restrict to requiring integer solutions, then there's something called Hilbert's 10th problem, which says that it's impossible to give an algorithm that will solve all such equations. You can't just give one that will take as input the equation and tell you whether or not there's solutions. So as soon as you get away from linear equations, you very quickly get in a situation where there's not a nice, clean answer like this, or even if there is, it might be there's finitely many solutions, and it's an extremely deep theorem that this is so, and we have no idea how to find it. Quadratic equations, fortunately, you can deal with those, but the theory is kind of tricky. But there is a way to deal with those. Okay, so let's do a few more examples. Let's do another example where we'll take the equation from before. It's exactly the same system, except I'm going to do one little thing, is I'm going to change the lower right number. I'll change the 7 to an 8. Okay? So I'm just going to erase the stuff I did here, and then change the 7 to an 8. All right, so now we have a new system of linear equations, almost the same as the one before, but it's different. One number is different. So what's going to happen? There's either going to be no solutions at all, a unique solution, or a one-parameter family of solutions, or two-parameter family of solutions. Without doing any further work, we know that it's going to be one of those situations. And let's just figure out what happens. But it's pretty neat that you know one of those things will happen. You just don't know which at all. Any guesses, by the way, before we go further? Okay, guess for no solutions. Any guesses for a unique solution? Infinitely many? All right, well, okay, just to be contrarian. Okay, so if you put this in reduced row echelon form, and I'm not going to do the whole thing again, since it'll be almost the same as before, except, well, that's what you get. There's a command in Sage called RREF, reduced row echelon form, and it gives you back the reduced row echelon form of the matrix. And so the first two rows are exactly like what we had before, I mean identical. They were the same to start with. But the last row, you get 0, 0, 0, 1. Maybe it's not too surprising that it's just one different, because when we started, all I did was change this by 1. What? That's right. How is that possible? So there's a system of linear equations such that it's equivalent, after doing a bunch of operations, to the completely valid system of linear equations, which is x1 minus x3 equal to 0, x2 plus 2x3 equal to 0, and 0 equals 1. This is a system of linear equations that I've written down. It looks like this. It's just that all the coefficients are 0 here. But you can put anything you want. So it's a completely valid system of linear equations. The question you ask about a system is, what is the set of solutions? So what is the set of solutions to this system? There aren't any. So there are no triples x1, x2, x3 that satisfy all three of these equations at once. Just because there's nothing, there's just no way to satisfy the last one. Okay, so we're done. Anyone who guessed that there are no solutions to this system of equations is right. And here we go. Okay. So I will just put a little indicator that there are no solutions. Or rather, the set of solutions is the empty set. No solutions. Okay? This is a symbol for the empty set. The empty set. Okay, so there's one. Now let's change an entry again and see what happens. So here's the next one. So what did I do? I changed the lower left entry to 17. Right here. Okay, and now I ask for the reduced row echelon form, and I get 1, 0, 0, and then it's really good that we didn't have to do this by hand, 1/11. I'll show you some examples of some random matrices that are just 10 by 10. All the numbers are really small in the input, and you'll see what the reduced row echelon form looks like. It's pretty ugly. There's a reason for that, which I will hopefully mention. But it's kind of hard to understand right now. So it's 1, 0, 0, and then 1/11, 0, 1, 0, 9/11, then 0, 0, 1, and then 1/11. Okay? So it's another system of linear equations started out looking like this, but it's equivalent to this one. And now if you write down the corresponding system of equations, how many solutions does it have? 1. Because it's really straightforward. It's just x1 equals 1/11, x2 equals 9/11, x3 equals 1/11. And that's one. There's one solution, and the solution is the triple 1/11, 9/11, 9/11, and 1/11. Okay, so this is an example in which you have exactly one solution. Okay. Oh, okay. Let's try some slightly bigger matrices, which I'll probably have to zoom out a little so you can see them. Yeah. So here, this is a random 10 by 11 matrix. I chose 10 by 11 because this is what you would get if you were to take a system of 10 equations in 10 unknowns. And you have that one extra column at the end. Okay. Just for excitement, I will change it, hopefully. Yeah, so now it's a different one. And now here's the reduced row echelon form. There it is. The calculation is pretty much instantaneous, but typesetting it on the screen takes time. So you can see the upper right entry is pretty big. Let me scroll down so you can see the whole matrix. And if you're in the back and you can't see anything, that's not good. So if you're in the back and you can't see anything, it's you take a random n by n plus 1 matrix in Computational reduced row echelon form. You'll see the identity matrix, and then a final column that has a bunch of really big rational numbers in it. So that's what you see. And that's what we're looking at on the screen right now. Okay, so there they are. You'll notice that the denominators seem to have something to do with each other. They're all pretty close. And the ones that are different are actually just off by a factor of like 2 or 4 or something like that. It turns out that there's a formula called Cramer's rule, which you may or may not have seen, but we'll probably see, which gives you an explicit formula for the solution when it's unique of a system of linear equations. And in that formula, you have a vector which comes from determinants of certain matrices. I'm not assuming you know what the determinant is yet, but if you do, it's some number associated to a matrix, kind of like, actually I haven't really associated any numbers to a matrix, but there's something called the determinant, which is a number associated to a matrix. And all of these denominators here, they're the determinant of the matrix on the left that we started with. So there is a reason that there's some common number appearing there. Just to show you a bigger example, let's try a random 100 by 101 matrix. And again, if you're at the back, well, just some big random matrix. So it's generated it, and in 0.1 seconds, Sage took that random matrix and put it in reduced row echelon form. And the very first row of the reduced row echelon form has, well, if I change the matrix, I have to show you what it is. But there it is. Just the first row is ones, then all zeros, and then at the very end there's one entry that's a big rational number. But note that it only took 0.1 seconds, which is pretty cool. And yeah, at some point I'll tell you something more about why it's able to do that so quickly, but even a much bigger matrix, so say 200 by 200, let's see how long that takes. The real question here is how much longer as a factor does it take? Is it twice as long? Is it 10 times as long? So it took 0.8 seconds instead, so it's about 8 times as long. The algorithm is roughly cubic that you use to compute the reduced row echelon form. Because what you do is you start with this entry and then you clear the column. That takes how many operations, how much arithmetic do you do? So if the matrix has n rows and n plus 1 columns, what you're doing is you're adding these n numbers to each of these other ones. So it's roughly n squared operations that you just did, right? You do n operations, and you do n operations again, and you do that roughly n times. So that's n squared operations. And you finish that one, then you do the next one, and again you're going to do roughly n operations. Maybe a little better, but if it were a big matrix, you're doing roughly n operations each time. And you have to do that all the way across the matrix, and the matrix is roughly n wide, so the total number of operations is n cubed. And so you can implement this in various ways, which will, there's a constant, but more or less the complexity is O of n cubed, which means that the time it takes, if you make the matrix twice as big, it'll be about 8 times as long. And if you make it twice as big again, then it's 8 times longer again, over and over. So it turns out, though, that via subtle techniques and tricks, it's possible to decrease this exponent by turning the whole problem of computing the echelon form into a problem in multiplying matrices. And using that, you can multiply matrices more quickly. Okay, so that's that. So that's what it looks like when you use big ones. What was the goal for today? Understand how to solve a system using echelon form and to see what some of the possibilities are. So do you feel like you understand how to solve a system? Sit down and solve a system. How about if you solve one? Really easy one, using exactly this process right now. Okay? Or tell me whether it has any solutions. Since you have several minutes, we'll do one and then we'll be done. So this is the matrix corresponding to the system. So the corresponding system via that correspondence. So the question is, are there no solutions, one unique solution, infinitely many solutions, and what are they for that particular example? Try it out. If you have any questions about what to do, just ask me right now. Anybody figured it out? Is anyone stuck? Or it's just tedious? Yes? I had fractions along the way, but then they disappeared at the end. Yeah, that's it. So for me personally, that's the biggest issue with this whole procedure is that you kind of start doing it, but then instead of getting all this confirmation that things are going right, like you do with, say, a crossword puzzle, you just get all this stuff which may or may not be going right. You can't really tell, which is really annoying if you think about it. Unlike a crossword puzzle, though, you can easily make up the puzzle. It's kind of nice. I just made this one up kind of at random. And suddenly everybody's stumped on a puzzle that I just made up at random. Well, not stumped, but... and you can be really careful, but... So when I did it, I just started adding the first row to the second and the first row to the third. And I immediately made an arithmetic mistake right here because I had to add minus 21 to 9. And I put minus 13 instead of minus 12. Oops. And so then I started continuing, and then I suddenly realized, wait, that worries me. And fortunately, I went back and fixed it. But that was already in the very beginning, the very first step that I was already messing things up. And if I got that one wrong and didn't fix it, then the rest of everything I did would be completely wrong. Yes?
How do you go from your second picture to your third and make it come third and then you have to make it fit?
This one, second to the third, from here to here?
Yeah. You have 1, 2, maybe 13.
Oh, sorry, that's minus 1/3. And then it became 13 there. Ha! Look at that. Yeah. So, yeah, look at that. So, my minus a third, my 1 was so small I couldn't read it, so by the time I went here, it became 13. Not good. So you can see how handwriting is a problem. But I was still confident in my wrong solution because there are infinitely many solutions. So right here, this is 1/3, 0, so then this is, so this has to be fixed. 2/3. Okay, and then it works. So, unfortunately, there's not a lot you can do to make the arithmetic easy, except you can, one thing that computers do is they work modulo a prime number p, and then there are no denominators, but you can still recover the right answer, which is, so it's like, computers don't do it with fractions like this at all, as it turns out. Nobody does it that way.
Question if we're able to, like, on tests and stuff, use calculators to reduce
Yes.
to row epsilon.
Yeah, but on the actual